In the name of God, the compassionate, the merciful, engineering plasticity, chapter 6, plastic analysis of torsion, part 4. We are going to talk about a method. In fact, we are going to introduce this new method called membrane analogy. Okay. In engineering, it is useful to use analogies. We use analogies in order to solve very difficult problems that cannot be solved in an ordinary way. We find similar phenomena which has the same mathematical equations, and we use those equations to solve the physical problems in hand. For instance, we have this torsional problem, so we are going to make this analogy with the membrane. Membrane is a very thin component, a very thin plate, let's say, and we are going to use this membrane analogy to solve the plastic torsional problem. So far we are solving the elastic torsional problems. We have not yet tackled any plastic analysis of the torsion. In here we have this membrane which is very thin. This is a membrane, okay, in the XY plane, and it is in the plane shape. The membrane is very plain, flat. That's the membrane in the XY, and that's the Z. And then we put pressure onto this membrane, which is here. This membrane is flexible, okay, it's flexible. So when we put pressure on it, because it's very thin and it's relatively flexible, it moves like that. It forms a dome-like shape, okay? So this S is the tension, okay? It's the tension on the surface on the membrane, and this P is the pressure. X, Y, Z are the Cartesian coordinates. Now here we consider an element A, B, C, D. Then the gradient of tension S in the AB side is given by beta partial Z to partial X. Let's see what we are saying here. We are saying that this S, which is the tension, now gradient of S in the AB side, so that side, on the AB side, because ABCD is an element on this membrane, so we are looking here at the in the direction of Z, so we see everything in a plane. So in the AB side, we say that the gradient of S is partial Z, partial X. Okay. The gradient is partial Z, partial X. And we call it beta. Since Z changes as one moves, because for instance, consider here, okay, we got partial Z, partial X is the gradient in here of this S. Now as we move along X, this changes. We have shown here that S, the gradient was like that, now it has changed to that. Then the gradient of the tension S in the DC side, which is this one, using the Taylor series, is given by that. So if we say that we were here and the gradient was that, now we are in here and the gradient has changed. How much has it changed? We say partial beta partial x dx. Yeah, that's how much it has changed. Now we can write this down as partial z partial x instead of beta, and putting partial z partial x in here, we get partial 2z to partial x2 dx. Okay, so that's what we get for this point on the DC side. Okay, AB side, DC side. And similarly on AD and BC side, we have the gradient. If we look at it in that direction, okay, it's very similar to this. We would have partial z partial y, and then at side BC we would have partial z partial y, similar to that, partial 2z partial y2 dy. Okay, so we get this gradient of s in the x direction and in the y direction. And now in here we have written the equilibrium equation in the vertical direction. Okay, equilibrium equation is the stresses and pressure times the area. Now the stresses are acting on this element are S in these directions, as you can see, and the pressure is acting this way. Of course, as you can see, this S is acting that way and it's acting that way, because any element on the membrane when under pressure, under internal pressure, is under multi-axial tensile stresses. Okay, it is stretched all over the place. So the S that I have put here, the direction is not in fact correct if we look at this element. Okay, but in general I have tried to show that the membrane is under tension, but if these two are tension, then this will be under compression. It's not correct. It should be something like that. Okay, so if that is the membrane is under the action of tensile stresses. Okay, so that's tensile. Because if it is compressive, the membrane is not able to withstand compressive stresses. It only can withstand tensile stresses. And because we have this pressure, internal pressure, the membrane is under tensile stresses. If you can imagine a balloon, these balloons, you will see that all the elements on the balloon, when it is blown up, are under tensile stresses. So that S should be that way. I will correct it later on in the PowerPoint. Anyway, if we take this into account, then S times dy, that direction, is negative direction in the negative x direction. So that's negative. Okay, that's negative times partial z to partial x is the component in that direction. So now if you look at this, in fact we are using the stress on this side, on side CD, and times the area here is dy. Okay, so S times dy is the force, and times the slope, so that we get the component in the vertical direction. Similarly, looking at these two stresses, then this stress times dx, okay, gives the force, and because it's in this direction it's negative, then times the slope gives the vertical direction, and on this one as well. On this one we get this, and therefore we can have also this P, which is the pressure, times the area, which is the area of this element, dx dy, because P is acting vertical. So this could be simplified to that. Okay, if we multiply that and we get P over S here, if we bring it over there and sort out all the terms, we get that, and neglect some terms, we get that. And this is Poisson's equation. We had this before, remember Poisson's equation, we had it for torsional problem. So here we have another problem, which is a membrane under the action of a pressure, and it changes its shape, and we get the equilibrium problem, and we get the equilibrium equation, and from the equilibrium equation we get the Poisson's equation. So we could use this analogy because we have the same equations for torsion and this membrane. So we could use this analogy to solve torsional problem. How do we do that? Now here we are going to compare the two problems. That's torsion and that's membrane. Okay, we are going to compare them with each other. Analogy means comparison. So let's see. In the torsional problem, we had this function psi. Corresponding to this function psi in the membrane is z, as you can see. So in the torsion, instead of z, we had psi. And in the torsional problem, we had this module of rigidity. In here, we have 1 over s. And in torsional problem, we had 2 theta. Remember, this equation was partial to psi here. And here was 2 theta g. So in here, we have, instead of P, we have 2 theta. Instead of 2 theta, in here we have P, pressure. And these were the shear stresses. Tau, partial psi, partial y, partial psi, partial x. But in here we have partial z, partial y, and partial z, partial x. Okay, note that here these shear stresses correspond to slopes, in fact, slope of the membrane after it has been pressurized. And the torsional torque, in fact, was this. Okay, we obtained this relationship before, and the corresponding relationship is this, is the volume. Volume under the that dome. Okay, volume under the membrane, pressurized membrane. Okay, so these are all equivalent. They are not equal, remember, because these are different problems, and so this has different dimensions. But they are different things. Okay, but they are equivalent. Okay, we can use this equivalency to solve a torsional problem because this is a simpler problem. Now, how do we do that? Now, before starting to solve a problem, let's have a look at these stress contours. Okay, because I said that this tau xz and tau yz are the slope, are equivalent to the slope of this membrane. Now, if this is the membrane and we look at it from the top, we can have contours like that, you know, there, and there, contours like that, looking at it from the top. And each contour has a constant slope. If you go, for instance, from here to there, all the way around, like that. On this contour, you have constant slope, and so you have constant stress. And therefore, for a constant z, because these contours are for constant z, that is the axis for z, and if we come here, for instance, z is this. So this contour all the way around, z is constant. So if z is constant, then partial z partial s and partial psi partial s are equal to 0, because they are equivalent. And therefore, partial psi partial s, what does it mean? Partial psi partial dy ds. Okay, so partial psi partial y is tau xz, and that is tau yz minus. So we get this relationship. Now this n is normal at this contour at an arbitrary point b. Okay, so if we write down, we would like to know what the stress is. So stress here at this point b is tau yz, okay, tau yz in that direction, tau xz in that direction. Tau yz cos nx, okay, nx and ny are these, cos nx is dx, dn, okay, because that's dx, and that's dy, okay, and that's the angle between them, and this is the normal at b, so dm is this bit. If that is dy, if that is dx, then dn is that bit. So cos nx and cos ny, we could write them as dx dn and dy to dn. Okay, and we knew from before that we had this, so tau is equal to that. Okay, and now let's solve a problem like a rectangular section. We couldn't solve the rectangular section before with the ordinary method, which we gave you, the St. Venant semi-inverse principle. We didn't solve for this, but also other methods we couldn't solve this, but we can solve it with this membrane analogy. So how do we do that? If we put the membrane on a flat surface and we make a hole, okay, we cut out from that flat surface this rectangular section. Okay, so we have a hollow rectangular section on a flat surface, and we put the membrane on the top of the flat surface. Okay, and we pressurize the membrane, so the pressure comes out of this hole, rectangular hole that we have made, and the membrane is fixed all over it. Okay, so we fix the membrane so that it touches the edges of the rectangle, and it is fixed to the edges of the rectangle. Okay, we fix it there, but in here is hollow, in here is solid. Okay, all over the rectangle is solid, but inside it is hollow. So when we pressurize from the bottom like that, this membrane goes like that. If you look at it from this side, or if you look at it from this side, the membrane bulges, okay, like that. That's the pressure, and that's S, and that's T. We are looking at it at this side, so we have this X, Y, X, Z. And for this sort of section, B is much greater than T. So the thickness is small, but the width is large. Okay, so that's what we have here, and we want to use the membrane analogy to solve this problem. So we have these equations as we mentioned in previous page, and what is the boundary condition here? Boundary condition is that z equal to 0 at x equal to t over 2. So x is equal to t over 2, that's the edge of the rectangle, and because we said the membrane is fixed at the edge, so it cannot bulge. It is fixed at this point. So at t over 2, x t over 2, z is equal to 0. Also at the middle in here, x equal to 0 is in the middle of this. Okay, so in here partial z, partial x is 0 because the tangent at the top is parallel to x-axis, so that is 0. After integrating twice, okay, integrating twice this equation, we want to integrate this equation, so we have half p over s t over 2 squared minus x squared using these boundary conditions, and also the volume under the membrane and in the xy plane. So that's the xy plane and the volume under the membrane. We want to know what the volume under the membrane is. That is the volume under the membrane, 2/3 of z max times bt, and this z max is maximum in here, and it is p over 2s, okay, from the previous page. So the volume, if we multiply all these together, we get pbt cube divided by 12s. Now this t is equivalent to 2v. In fact, as we said before, t is the torsion and 2v is the volume under this membrane, okay, precious membrane. Here note that we have put the equivalence for p and s from that table that I gave you, okay. So that's why we got here g theta and bt cube g theta. So instead of this p over s, we have put this g theta, and that's what we get, okay, for t. That's in fact t is equivalent to 2v, but t is equal to that. And so maybe it was better to write 2v is equivalent to t and t is equal to that. Okay, that would be a better notation if I do that. Therefore, 2v is equivalent to t and is equal to 1/3 of bt cube g theta. Now torsional stiffness. Also remember torsional stiffness, we said, we introduced this before. Is t over theta, so it's 1/3 bt cube g is j g, and tau is equivalent to partial z to partial x and is equal to 2g theta x, and theta is equal to 3t bt cube g. So at x equal to t, we have the maximum shear stress, because here we have the maximum gradient, and therefore tau max is equal to that. Tau max is equal to g theta t at x equal to t over 2, and then the torque t is 1/3 of bt squared tau max, okay, because here we have put substituted for that. So note that in here we have solved this problem very easily, but we should note that at this at this table. For instance, we have in the equations that we have equivalence, we put instead of 1 over s, we put g. Instead of p, we substitute 2 theta. Instead of z, we substitute psi. Instead of partial z, partial y, substitute this. So that's how we solve these problems.